All right, welcome back, class. Here we are, lecture 6. What will be our swan song in the discussion of density fluctuations and liquid structure. We've finally come to the point where we can kind of gather everything together and work out a complete theory now for the structure of a fluid and therefore how a fluid responds, both of which are encoded in that density-density correlation function. So we're going today work out a theory, a self-consistent theory for a hard sphere fluid, a simple fluid in which there exists an exactly solvable prediction for the G of R under these Gaussian field assumptions, which essentially will make it valid away from very high densities where even a hard sphere will crystallize, crystallization therefore being a very nonlinear response. And we'll touch briefly upon how you go beyond just hard spheres, either including back electrostatic interactions, valid within a theory known as the mean spherical approximation, or how you use as input the G of R with this Gaussian field theory to then predict solvation for energies for ideal hydrophobes. Ideal hydrophobes being just particles that exclude volume. Before we do that, last lecture we ended with a brief discussion about Monte Carlo, showing you, elaborating on a little bit how you can actually study a system of hard spheres, which you'll do in your homework. I wanted to walk you through that code before we get into the details of this current lecture. Okay, so here's the code that I'm going to upload to B courses. It's a Monte Carlo code. It's written in Python and uses a couple libraries like Numba and NumPy, Matplotlib, to make it go fast. So if you don't have Numba, which many of you might not, that's a special package, your code will run a lot slower, but you can still get it to work by commenting out that Numba line. The code sets up a periodic lattice in this initialize function, and then performs the Monte Carlo we discussed before, namely by drawing random displacements, maximum size delta, and looping over all n particles, first uniformly drawing one of those particles, then taking that particle position and making a random update, invoking periodic boundary conditions so that we have a reasonable representation of the bulk fluid in both the x and y directions. Then we will call a Metropolis acceptance criteria with those initial and final or trial configurations. In a hard sphere, the acceptance will be with probability 1 or 0, depending on if there's an overlap. So we need to compute whether or not in the trial configuration there is an overlap. If there's not, we'll return 1. So here are some example parameters for a 100 particle system in a box that's 144 square sigma squared units. I've written a little function that will let you actually see the system and produce little drawings over the course of some in sweeps through the lattice. And so let's just go ahead then and print out using this image flag that being set on and see what that would actually look like. So running the code, let's make it bigger so you can see. Python executing this code just with Python hard sphere mc.py. You will see a fairly dense system with a single tagged particle that just help you watch it evolve, fluctuating around, exploring many thermally accessible states here. Thermally accessible just means that there are no overlaps. And as you might expect in a liquid, motion is largely diffusive. There's no long-range order. The structure is disordered. And we can just pull up a picture just to show you what an example final configuration might look like. And then it'll look like that. So you'll be tasked with taking those snapshots, using this code, and actually computing the G of R with it. as well as studying some density fluctuations to confirm the assertion that we've made in a lot of what we've been discussing, in that the density fluctuations in a fluid really are Gaussian. So those are things you'll be able to do with this code. You'll have to implement those routines. So actually take the configurations generated from this Monte Carlo and, as guided through by the homework, actually compute those both the distributions of density fluctuations as well as the G of R. Okay. So that will give you a radial distribution function for a dense fluid of hard spheres that you'll actually be able to compare to when you work through the theory that we're going to present in today's lecture. Okay, so here we are. We're going to discuss in this lecture a Gaussian field theory for density fluctuations and therefore liquid structure. So the aim of this theory is to have an analytical route to the prediction of the G of R, the density correlate, the non-trivial part of the density correlation function. As we elaborated on last lecture, with that function in hand, we have access to the thermodynamics of a fluid. So we will work under the assumption that we have been in a lot of this part of the class, which is that the statistics of the density field are Gaussian distributed, which means that provided the system is at thermodynamic equilibrium, I could represent the Gaussian statistics of the density field with an effective Hamiltonian, which is bilinear in the fluctuations in the density. So the density is defined over points R. I'll look at a fluctuation at R, a fluctuation at R prime, and these are correlated with the correlation function chi of R and R prime. So putting this function on the right-hand side of that equation into an exponential gives us a Gaussian distribution. Associated with this Hamiltonian would be a partition function, which is an integral over all spatial density fields, all ways that density could fluctuate, weighted by this effective Hamiltonian. Okay, so this is the setup. So we have something looks kind of scary. It exists in a field. That field is fluctuating, but hidden underneath all of this is just a really gussied up harmonic oscillator. It's a correlated harmonic oscillator. So we're not expressing the Hamiltonian in the normal modes of the density. More on that in a bit. But as you have worked through in your homework and as we have elaborated on in class, one can treat correlated random variable, Gaussian random variables within a change of basis, within a normal mode representation, and then compute in an uncoupled set of harmonic oscillators or harmonic Gaussian variables, anything you want, including this partition function. Now, the partition function itself is not actually what we really care about. What we want to know are things like what that chi function is. How do we write down an equation that will actually tell us what chi is? Well, that is closed, which we can use to solve for chi in the same way we did with the Debye-Huckel theory we've already presented. So to do that, it will behoove us to introduce an external field that then whose expectation will give access to a cumulant generating function for moments of the density field. And we know that that chi function, that correlation function, is just a second cumulant of the density field. So let's call the field phi of r. It enters in to the statistics of the density, to alter the statistics of the density field in a way that is linear or conjugate to the density. So we have our original effective Hamiltonian, and we'll add to it an integral over all space, phi of r times rho of r. Integrating that weight over all density fields gives us a partition function now in the presence of that phi. As we have demonstrated now a number of times, that partition function in the presence of phi is going to be equal to a partition function in its absence, now times an expectation value of this extra bit, the phi multiplying rho summed over all space. And if the density field is Gaussian, that's a Gaussian integral that we can do. Remembering that if we had P of y as e to the y squared over 2 sigma squared, properly normalized, the integral call it I, the integral over y, P of y, e to the ay is equal to, by completing the square, e to the a squared sigma squared over 2. So that's the single dimensional Gaussian integral whose field variant, whose multi-dimensional variant here, we are now going to evaluate. And we can essentially evaluate it by pattern matching if you don't want to go through all the algebra. The partition function in the presence of the field will be proportional to exponential of 1/2. Now playing the role of a is phi of r. It comes with an integral, so we have to integrate over r. A gets squared, so we have to integrate over r prime. A phi of r, a phi of r prime. Playing the role of sigma squared is chi. So we have that correlator sandwiched in between. And now there's a slight difference in our red integral in that if we had a non-zero mean, as we do in the density, there is another term that would act like phi r times the bulk density. Again, easily done by just completing the square. Okay, so that's our cumulant generating function for the density field. And we can convince ourselves that as a cumulant generating function, the functional derivatives of log of Q with respect to phi of R evaluated with phi is equal to 0 will generate the cumulants of the density. The first cumulant of the density is just its average. For an isotropic fluid, the average density, there's no conditioning here, is just the bulk density. The second functional derivative of Q with respect to R, phi of R, and phi of R prime, evaluated where phi is 0, will bring down the second cumulant, in this case the correlation between fluctuations at rho at R and fluctuations of rho at R prime. In our reference, which is just our chi function. So by evaluating Q, we've gotten an expression or a route for chi. Now chi, in this case, there's no way to solve for it. It was put into the theory. This is just showing that that insertion is self-consistent. So now we need to think of a way to ask for the response of a fluid determined by this chi, which then gives us a route to solving for chi. So we can follow a procedure very much like we did with Debye-Huckel theory. Remember, Debye-Huckel theory, we took an original fluid, which had some density-density correlation function. In this case, there were a set of ions correlated with some G of R. And then we imagined growing in an ion at the origin, asking for what the density in the vicinity of that ion was, invoking self-consistency gave us the G of R on one side of the equation and on the other, which we can then solve for. So we're going to do the same thing here with an important exception. In Debye-Huckel theory, our usual linear response, adding in a potential for how the ions interacted, in order to invoke linear response, we had to assume that that potential was small, that it was perturbative. If we were to grow in, and that is a reasonable assumption under dilute solution conditions where the ions don't interact very strongly, they stay on average far away from each other. If we want to actually solve for the structure of a liquid, excluded volume is going to be an important component of that liquid. In fact, we elaborated on the structure of a fluid last lecture, essentially only invoking the fact that they exclude volume. Excluded volume is a very strong perturbation. On its face, it comes with a potential that says, for a hard sphere, for example, that it is infinitely unfavorable to have an overlap. That doesn't sound like a small perturbation, that sounds like an extreme perturbation. And indeed, if we pushed our Debye-Huckel theory, in which we treated the potential as the perturbation directly, away from regimes where it was perturbatively correct, we saw unphysical answers. So for concreteness in Debye-Huckel theory, if you start asking questions too close to where the ion would exclude volume, so it's small r, we found that the G of R would be predicted to go negative, and that's of course not true. So we need a different route of perturbing the fluid in a way that we can still use our Gaussian field theory, but is not perturbative in a simple way, not just adding a potential. And the way to do this is that rather than just adding a really strong potential and asking for the response to that, we are going to add a constraint. We're going to tell the fluid that it just can't occupy some region of space. So the picture I want you to have in your mind We have a fluid here. It's made out of a dense, not a box, a dense solution. So there are, in this case, let's just for concreteness be imagining that this is a fluid made out of hard spheres. So there's a bunch of spheres here. They're all identical despite my drawing. Right, like so. They all have centers and diameters, call it sigma. And now let's take that fluid and carve into it some region. Call it N, that we're going to say there is no density. So we can grow in that constraint much in the same way we grew in an ion in Debye-Huckel theory. And if there's no density there, after we've grown in, we've invoked or applied that constraint, that is then a space that a solute could occupy. So this is the picture. We have a dense fluid. The density, let's say that red sphere that we're going to grow in is located at the origin. Without the constraint, the density a distance r away from the center is just the bulk density. Without the constraint there, every point in space is equal to every other point in space, so the density is just uniform. With that constraint, with the solute excluding volume at r is equal to 0, we can then ask, how does the density evolve under that perturbation? So this should look a lot like Debye-Huckel theory, growing in an ion at the origin, seeing how the surrounding ions respond, with the important difference that we are not growing in a potential and asking for the response of the density. We are going to grow in a constraint that says there is no density of the solvent in this region. So it's reasonable then to ask, why will a linear response theory tell us about the response to this constraint? And that comes from the mathematical form that the constraint will take. So mathematically, we can invoke a constraint that there is no density in some region by applying a delta function whose argument returns 1 only if rho of r is 0. Now we want that rho of r to be 0 over a whole set of points r in this N region we've defined in red. So let's denote that r in the N region. Now again, a delta function looks like a pretty non-perturbative thing to apply to the fluid. However, if we note that the delta function, even of a field, has a Fourier representation, let's introduce that Fourier representation by introducing a conjugate field psi of r. That's kind of like the Fourier variable to a normal Dirac delta function definition, we have an exponential, which is complex, that psi of r is conjugate to what the argument of the delta function is, in this case, rho of r. And there's a whole sequence of a product of delta functions, which means that there are a product of exponentials, or an exponential of a sum in a continuous space is an integral for all r's in that region N. Now, isn't this interesting? That constraint looks like an exponential of a function linearly conjugated to the density. So that looks just like a linear response setup we would have if we were applying a potential that was linearly conjugate, actually acting on the density. So viewed in the right light, a constraint is like a linear perturbation, with an important difference that we'll see shortly, that unlike just adding a linear field or force to a variable, a constraint will actually change the fluctuations of that field in a way that adding a force does not change the spring constant or the fluctuations of a harmonic oscillator. Okay, so that's how we'll impose that constraint. So let's set this up. So in the presence of the solute that acts only to exclude volume, or rather to constrain the solute density, solvent density, to be 0. We can write out the partition function in the presence of that solute, still in the presence of some conjugate variable to the density phi, such that we can still get a generating function out of this calculation, which is now an integral over this auxiliary field psi, an integral over the density field rho, our Gaussian model for the density field, our phi field that will give us a generating function, and finally our constraint that introduces this psi function linearly conjugate to the density. Okay, so we just did the integral over the density field when we just had phi. The integral is of the exact same form when we've introduced psi. If we add phi and psi, that is together just something that acts linearly in opposition to rho. And so integrating over those Gaussian fluctuations will give us a form very similar, though now under the integral over psi still, than what we had a second ago. So doing that Gaussian integral, the partition function is going to be proportional to the exponential of 1/2. We'll have what we had before in the presence of phi, an integral over r, an integral over r prime. I'll adopt this little subscript notation just to save some space. I'll have phi of r, chi upright, r and r prime, phi of r prime, plus phi of r rho bar. Now all of that is independent of psi, so it can be pulled out of the psi functional integral. Underneath that integral, or all the terms that have to do with psi. So we'll have a piece from the average value of rho. That'll be I integral over R. Let's stick with our subscript notation, R in the n region, psi of R rho bar, minus coming from the I squared term, 1/2 integral over R prime, psi of R, chi of R and R prime, psi of R prime, where both of these are in the n region. So that's just like doing the integral with phi conjugated to rho twice, with the same sort of form, just with restrictions over one of those integrals. But in addition, we'll get a mixed term, I integral R in the n region, integral of R prime everywhere in space, psi of R, chi of R and R prime, and phi of R prime. Okay, so we have now, just kind of like we've done two generating function calculations where we have the phi and psi squared pieces, and now a mixed piece coming from squaring the sum of phi plus psi. Looks ugly, but I think the bones of it are straightforward. Let's, for simplicity, define the function f of r as an integral over r prime, chi r, r prime, phi r prime, in which case q sol, the partition function in the presence of the solute, is proportional to q in the absence of the solute, an integral over psi of r, that conjugate field, the auxiliary field whose integral resulted from the Fourier representation of the delta function, exponential 1/2 r in the n region, r prime in the n region, psi r, chi r and r prime, psi r prime, plus I integral in the n region, rho plus f of r, rho bar plus f of r. So again, just for concreteness, this is the partition function without the constraint, or without the solute. All right, so our job is not quite done. We had to introduce this extra functional integration over the conjugate field psi of r to impose the delta function constraint. We don't want an answer with that field still there, so we have to perform the integral over psi of r. In principle, that looks like it should be, that sounds like it's a complicated thing to do, but note the structure. The functional integral over psi of r is bilinear in psi with a chi of r and r prime sandwiched in the middle, and a linear additional piece. So overall, it's just another Gaussian variable, a Gaussian distribution just now in the psi variables, which means that we can integrate them out further. Now, there's one subtlety here. This chi, our original chi, is defined for r and r prime, where r and r prime could be anywhere in space. It became inverted when we did the first Gaussian integral over the density. To invert this function now, it's defined only over a restricted space, for r has to be in the in region and r prime has to be in the in region. Its inverse now is not going to be just the inverse of chi itself. We need to define a new functional inverse for inverting that chi in the restricted region of r and r prime in the in region. A functional inverse is always defined like so. Let's integrate over. Sorry, my screen's having a hard time here. Let's try this again. Let's integrate over some field variable r double prime just in the in region. The chi inverse restricted to the in region is then defined through an integral relation in which I integrate over one of its variables times the chi original function. This then must yield a delta function of r minus r prime, provided r and r prime are both in the in region. So that's a definition of the functional inverse we'll need when we do the Gaussian integral over the field psi of r. So doing that, q sol is going to be proportional to q without the solute and exponential. So now the linearly conjugate object to psi is the bulk density plus this function f of r. So that's what's going to enter in bilinearly to this Gaussian integral. We'll get a minus from the I squared in front of that linearly conjugate function to psi of r, an integral over just the in region, another integral over just the in region, rho bar plus f of r, a chi inverse defined only over, or inverted only over the in region, and a rho bar plus f of r prime. All right. So now we have our whole cumulant generating function in the presence of the solute. It's proportional to the partition function in the absence of the solute. It's worth noting a connection to the thermodynamics of solvation. So it is always the case that a ratio of partition functions, say of the solute without the applied field, or the solution in the absence of the solute also with no applied field, a ratio of partition functions, if I take a log and a minus, always has an interpretation as a change in a free energy. So what's changed between these two systems? When one I have just a pure solvent, in the other I've added a single solute. So the change in a free energy upon adding one particle, that's what we call a chemical potential. Oh boy, sorry. And in this case, it's in units of beta. So this is the chemical potential for adding these solutes to the solution. For those versed in ideal solution theory, if there's only one solute, that's an ideal solution. It would have a contribution from all the different ways I could put that solute in the solvent, all the different spatial arrangements. That is not this piece. This is pinning the solute to one location. And so this is the excess or standard state, a means of computing the standard state chemical potential associated with that solute. And we have an explicit equation for it from this line up here. It is just the bulk density squared over 2 and 2 integrals over this n region weighted only. So if we evaluate this line here without the external field, those f of r quantities go away. So we're left with just bulk rho squared integrated over chi inverse. We've written these things as proportionalities. There is some overall normalization that we've not added, but it's the normalization just of a Gaussian distribution. We know that that looks like a square root, which on a log scale gives you a factor of 1/2, a 2 pi, and usually the normalization of a Gaussian distribution would be sigma squared, but playing the role of sigma squared is chi n. And there are multiple sigmas for the different field points that we have fluctuations in. So this is the chemical potential for solvating a hard sphere, for which we have found by just excluding density from some region and finding the thermodynamic cost associated with excluding that density. Now, there are no energies here. There's no potential we applied. So this change in the chemical potential for solving a hard object is purely entropic. So there's an entropy change associated with restricting the places that solvent density can be. In the Gaussian field, we find that this is something that just goes like the probability of evacuating that density field, which should just depend on how many particles are likely there. That's something like the bulk density squared, and the curvature associated with that distribution, which is something like this chi inverse integrated over space. Okay, but back to the generating function. If we take a derivative of log of q sol with respect to phi of r, keeping it back on for the moment, and if we then evaluate that derivative at 0 as a cumulant generating function, this gives us the average density at point r, now in the presence of that solute. So we break translational symmetry by pinning the density to be 0 at a specific point in space. There are therefore a response of the density in the vicinity of that constraint, yielding an expectation value of the density at some point r, which is not necessarily just the bulk density. In fact, taking the derivative from this line here. The derivative, remember, these f of r functions are defined as phi. So it's like taking the derivative of the f of r. So taking that derivative, we'll have one contribution just from the bulk density. We'll have a bulk density integrated over r in the n region, r double prime in the n region, chi of r and r prime, and chi n inverse of r prime and r double prime. Now that looks a lot different from the relationship we got with Debye-Huckel theory. Remember, Debye-Huckel theory, we ask for that average density in the vicinity of a solute 2. The first term looks kind of similar, the bulk density, but the second term looks much more complicated. However, if we define the function c of r as minus rho bar integral over r double prime restricted to the n region of this chi inverse of r double prime r prime, if r prime is in the n region, and 0 if r prime is not in the n region, we could substitute c of r into this expression for the average density, and we find that the average density away from the solute pinned at the origin is equal to rho bar plus, because I've introduced a minus, an integral over all space, because I've set explicitly to 0 the contribution when c of r is not in the n region, or r prime is not in the n region, chi of r and r prime, c of r prime. And now that looks exactly like what we had in our Debye-Huckel theory. If we had a phi of r, which was minus kbt c of r, that result is exactly like Debye-Huckel theory. However, there's a really important difference, the important difference that is manifesting in the introduction of this correlation function defined, or whose inverse is defined over some restricted region of space. Specifically, there's an important difference between this theory and Debye-Huckel theory. If we took two derivatives of the cumulant generating function with respect to phi of r, we would be able to generate the correlation function between density at 2 points in space, now in the presence of the solute, taking the derivatives of this function here with respect to phi at r and phi at r prime. Notice we'll get contributions that look just like, again, f of r has a chi in it, so there will be chi functions there. Those are multiplied by this chi inverse. And so if we did that, we would find that the correlation function has a component of what it had before. But in addition, we have an integral over some other point in space, call it r bar, in the n region and another point in space r bar prime in the n region, chi of r bar, chi inverse in the n region of r bar and r bar prime, chi r bar prime, r prime. Which is to say that the fluctuations, the correlations, change due to the constraint we've placed on the density field. So this is not your mother or father's linear response theory. This is something really different. This says that we apply a constraint and the fluctuations change. Again, to remind you, if we added a perturbative force to a harmonic system, the fluctuations do not change, they encode response. Here, we add something that looks like its linear response. It enters into a Boltzmann factor in a way that is linearly related to the fluctuating variable, in this case, the density field. And yet, by adding the constraint rather than the perturbation, we do actually change the modes. We change the correlations between the density. In fact, the condition we've imposed on the density looks like that we've enforced that if we integrate chi over r prime, weighted by this C of R function, which again, C of R has this chi inverse in it, we've constrained that integral essentially to be minus the density for all R in the N region. I like to think of this in terms of harmonic systems. Imagine I have a drum. If I push on the drum, I will generate an elastic deformation away from it. But the mechanics of that drum don't really change. If I push on a small way, I can still tap on it in different places in space, and it will sound the same. That's like normal linear response. This constraint is like cutting a hole in the drum. The modes change. The sound of the drum would be very different. So this C of R is a field due to the solute that causes the density to go to 0 on average, and is known, it's worth giving it a name. It's often known as the so-called direct correlation function. Essentially, in analogy to how it looks like it enters into an equation for the full density correlation function in Debye-Huckel theory, that C of R is replaced by a potential. It is a direct interaction. In this case, C of R is not an interaction, and so one uses kind of a hybrid nomenclature and calls it a direct correlation function. It was essentially something that was introduced in the 70s and with people trying to work out theories of liquids, essentially by fiat. People knew Debye-Huckel theory work, wrote equations down that looked like Debye-Huckel theory, and then played games to guess what sorts of functional forms C of R should take in order for them to both solve the equation and additionally get a reasonable characterization of the structure out. We now understand what exactly it is. It has to do with the change in the correlation function due to this constraint. There's a simple way to understand how it is that these modes change and can get a kind of a representation of the fact that the modes change. by actually diagonalizing our original Hamiltonian. So a way to get an intuition that this should indeed be the case is to note that our original Gaussian effective Hamiltonian for the density field as a set of correlated Gaussian random variables can be diagonalized by introducing a set of normal modes of the density, which are its Fourier components. So the isotropic fluid having translational variance and being bilinear should tell you that a Fourier transform should decouple these functions. Indeed, if we introduce rho hat of k being an integral, or let's define rho, delta rho of r being an integral over k. Let's denote it with this sort of subscript, which includes any factors of 2 and pi, a delta rho hat of k, and e to the I k dot r. So we can introduce a Fourier transform of the density field like so, defining these functions delta rho hat of k. If we introduce that and additionally introduce a Fourier representation of chi r minus r prime as an integral over k chi hat of k e to the I k r minus r prime. Essentially, we have a couple convolution due to the fact that chi depends just on the relative distance between r and r prime. This means that when we introduce those Fourier transforms, we will get a couple delta functions that will reduce this into a single integral over k. Let's keep that subscript notation. A modulus of the Fourier transform density squared and a chi inverse of single k. So now that is diagonal in k. So indeed, this looks like a set of uncoupled density fluctuations. So each row of k fluctuates independently with an effective spring constant, which is chi inverse. Indeed, we can read off delta rho of k magnitude squared and average as just chi of k, which is diagonal in k and thus has an inverse which is trivial to compute. So this looks really like a harmonic oscillator system, a set of uncoupled modes. So in that Fourier representation, we could think through what a constraint would do. So let's imagine in our free harmonic system, we do really make an analogy to a harmonic oscillator. So let's imagine we have a little trimer coupled with two springs. The normal modes of a trimer, if these really were harmonic degrees of freedom, would be a symmetric and anti-symmetric stretch. So I'd have some symmetric stretch where those two molecules move away from the central molecule, and a asymmetric stretch where they move in the same direction. Now, of course, this is a bit, the direct connection is a bit abstract. We're thinking about these modes as density modes of a fluid, but they are connected to each other with simple springs, since we've just diagonalized that field. So now let's imagine we take that trimer analogy and pin it such that this middle particle can no longer move. If it is infinitely restricted, now the normal modes are uncoupled. I'll have one normal mode, which just moves that right particle to the right, and another normal mode that moves that left particle independent of the right particle. So think about that. You might, I don't know if you have slinkies lying around, but if you do, you could actually grab it, see its mode structure by bending it around, and if you clamp it down in the middle and try to vibrate it or fluctuate it around, you'll know that the way it fluctuates or responds is very different. It can't be written as a superposition over the unconstrained fluctuations, unconstrained modes. Okay, so this has given us an ability to now write down a closed expression or a theory for the structure of a solvent around a solute, a hard solute, which just excludes density. These sort of equations are known as integral equations. So reprising our result from above, the density in the presence of the solute, or the density constraint, is the density that would have been there in the absence of the constraint, just bulk density, an integral over some intermediate position, the correlation function times this C of R function. Now this is not completely closed because we don't know, we could ask, for example, what is chi? We know that chi takes a representation or is decomposable into a piece that is diagonal and a piece that has to do with the G of R. So one way to think about what we're doing is to imagine that the solute that we place in the origin, the hard particle, is identical in form and shape to the solvent. So imagine that the solvent is made out of hard particles of the same size as the solute we've grown in. If that is the case, then the statistical equivalence to the density around the solute, or that hard particle, says that the right-hand side should be the density conditioned on there being a solvent particle at the origin. So that should give me back the G of R, which is on the left and now on the right. So again, using the notation H of R being a G of R minus 1, we can get an expression for the H of R of the solvent being equal to the C of R plus rho bar, integral over intermediate positions, h of r minus r prime, c of r prime. So now we have a self-consistent equation for the structure of the fluid by imagining that the solute is really just the same kind of particle as the solvent. This equation is known as the Perkus-Yevik equation. It dates back to something like 1958, when structure of a fluid was really a hot topic. It's not still completely closed because this C of R function, if we remember what C of R is, has a chi in it still. In fact, it's got the functional inverse of chi restricted to the N region. A way to solve, so the functional inverse, where did we put that? Sorry, here we are. This equation here, the definition for chi n, is to define that functional inverse rather than looking at the integral expression of that functional inverse. If I took derivatives on both sides, I can actually write down an ODE that chi n would have to satisfy. So actually chi, some of you might recognize this sort of structure. These chi's are Green's functions. So Green's functions can be written in solution. Green's functions can be evaluated either by integral theories or from ODEs, their unintegrated form. This is to give you some intuition that to solve for this chi inverse, to do the functional inverse of this function, one will need to apply boundary conditions. It took about 5 years for people to work out what boundary conditions to apply. If we say that C of R is equal to 0 for R greater than sigma, so that is outside of the N region, that chi inverse is not defined, it's set to 0. That's indeed what we mean. And that h of r is -1 for r less than sigma. That invokes the excluded volume constraint. So h of r is g of r -1 for distances less than the excluded volume distance sigma. The g of r should be 0, or the h of r should be 1. So if we apply these boundary conditions, which a guy named Wertheim did in 63, I don't remember how you solve Wertheim. I think it's IEM. Pretty sure it was 63. I'm sure this is written in the notes somewhere. He used those two boundary conditions to then solve for what the C of R is, and in doing so, solve for the H of R. So the C of R takes a form of constants, lambda 1 and lambda 2, times R in units of sigma, plus a lambda 3, R in unit of sigma raised to the third. Again, this is only defined for R less than sigma, where these lambdas are expressible in terms of the packing fraction. Call it eta. The packing fraction for a three-dimensional fluid is pi over 6 times rho times sigma cubed. Lambda 1 is -1 plus twice eta squared over 1 minus eta to the fourth. Lambda 2 is 6 eta 1 plus eta by 2 squared 1 minus eta to the fourth. And lambda 3 is simply related to lambda 1 by a factor of eta by 2. So there's an exact solution for C of R. And just like we solved Debye-Huckel theory, if we know C of R, we just have some Fourier transforms to then solve for H of R. In fact, if we Fourier transform both sides, we'd have H hat of K is equal to C hat of K 1 minus rho bar C hat of K. C of R is just a polynomial in R. It has a Fourier transform, so that's fine. It turns out that there's not a simple algebraic or analytical form for H of K that is, easy to write down. But given everything else, it's still a closed theory. It's still, straightforward to evaluate numerically by doing the numerical inverse Fourier transform. Note this sort of structure of the H of K being proportional to Fourier transforms of C of K also has a fancy name associated with it. It's called the Ornstein-Zernicke equation. It was introduced early in the study of liquids, especially liquids near critical points where correlations diverge and one could associate simple solutions, simple so-called closures for what that C of R might look like. Indeed, there was a whole cottage industry of trying to solve these integral equations for liquid structure, moving beyond just hard spheres. One could introduce boundary conditions that said that the C of R was equal to some potential that was attractive for R greater than sigma. And the H of R still invoked that excluded volume constraint for R less than R sigma. This is known as the mean spherical approximation. It's essentially a way to include the Debye-Huckel equation, in which case we would have exactly replaced this C of R with the potential that the particles feel, with the additional constraint that we exclude volume. So this is valid for, so actually the mean spherical approximation works quite well for electrolyte solutions up to concentrations of like 0.1 molar, maybe a half molar, whereas Debye-Huckel theory breaks down well before 0.1 molar. It's only valid up to about 1/100 of a molar. What was not clear, why there's such a cottage industry of developing boundary conditions and trying to work out solutions for these sorts of integral equations, was because this underlying Gaussian structure was actually not appreciated. We know that all we need to do is solve this inverse problem, this functional inverse, to get this C of R. C of R was posited in the early days of liquid structure or liquid state theory phenomenologically. People didn't know what it was. They stuck it there to make it look like a Debye-Huckel theory and then tried to associate with it different functional forms, different asymptotic behaviors. And sometimes they worked and sometimes they didn't. No one really understood what the underlying theory was. And it wasn't until David Chandler wrote a paper in 1993 that tied all of these sorts of theories together with this kind of underlying Gaussian field commonality. In fact, he used a similar sort of theory to first explain the hydrophobic effect. So we have treated this theory imagining we want to solve for the radial distribution function. We wanted a closed theory for the structure of a fluid. If we went back to not having this being self-consistent, but imagining that the solute was something different from the solvent, like imagine the solvent was water, we could add in this constraint on the density of water and ask for how water reorganizes around some ideal solute. Just translating the labels we found for this theory into that case, what we would need to determine how water reorganized around that solute is the correlation function between water and itself. So this is the density of water away from a solute. This is the water correlation function. If instead we imagine that that correlation function is empirically known, like measured with an X-ray scattering experiment, we could use that empirically to determine the response of water to these solutes. C of R is just determined by that functional inverse. So again, that could be done numerically. And if we are not so interested in the density of water around the solute, but rather just that chemical potential was just given by a simple functional form. We go all the way back here. We just need to know chi inverse. So we need to functionally inverse the water G of R over this restricted in region defined by the size of a solute. We can predict solvation free energies for ideal hydrophobes in water. Indeed, this was known as the Pratt-Chandler theory of the hydrophobic effect. That dates back to 1977, I think. And actually works very well. You can predict small alkane hydrophobic energies pretty quantitatively with the empirical knowledge of the water radial distribution function. So taking a bit of a step back here, we started with a simple but profound assumption that density fluctuations in liquids were Gaussian random variables. That let us write down an effective energy function for that density field that was parameterized by a correlation function, a density-density correlation function, and a bulk density. That correlation function determines the response of the density, so it is a useful quantity to know. And if we did just know it, we could perturb the density by adding a solute and find out its response, which could be quantified either in how the solvent reorganized around that solute or through the relationships between structure and thermodynamics, what the chemical potentials or reversible works are for solvating those solutes. But more interestingly, we can turn that calculation of response around and actually use it to give us a self-consistent expression for determining that density-density correlation function itself. So treating a solute or labeling the solute as the same kind of atom or molecule as the solvent that made up the solution by asking for the density response of adding in that extra solvent molecule now, that being proportional to the density-density correlation function, we get a self-consistent expression that in some cases is solvable exactly for the radial distribution function of that fluid. Simple analytical theories have been found for hard sphere fluids. One can get some analytical traction in this mean spherical approximation, so adding for Coulomb potentials, so adding slowly varying attractions. And to the extent that fluid structure is determined just by excluded volume, successful liquid state theories going beyond this, going beyond hard spheres, essentially try to map more complicated fluids to hard spheres for which these exact analytical results exist. You will, in one of your upcoming homeworks, actually use the Perkasiewicz theory, do the Fourier transforms numerically, and actually see that really the radial distribution functions predicted by that are quantitatively accurate over a very large range of densities. The intuition that this is a linear response theory should tell you that there is going to be cases where growing in that solvent molecule is results in nonlinear effects. And the intuition for where that should happen is where nonlinear effects are large, and those are going to be near phase transitions. So for a hard sphere fluid, the only phase transition that exists is crystallization. That occurs at high density, so Perkasiewicz theory indeed is found to break down at higher densities. It can't predict, because it's a linear response theory, it can't predict something nonlinear like freezing happening, although people have tried, not understanding this underlying Gaussian theory structure. Okay, so this is really all I wanted to say about the structure of fluids. It has given us insight into Gaussian fields. In the next couple lectures happening next week, I'll give you other examples of Gaussian field theories that are used commonly. In the case, we'll find cases of solvation, if you will, of quantum particles in solids. That is a Gaussian field theory first worked out by Feynman called the Polaron problem. And also we will work out a field theory, a Gaussian field theory for membranes, so lower dimensional objects, and how solutes embedded in membranes generate effective attractions because of this observation we've made, which is that by adding in constraints to a field, you change the modes. You can then imagine by where I put those constraints can change the thermodynamics and thus generate effective attractions between particles embedded in this solvent, or in this case, a membrane, which we'll talk about next lecture. All right, that's all I got. Sorry for going a little bit long this week. I'll try to make up for that by going a little bit short later on. All right, I look forward to seeing everybody in small group discussions, and I hope you have a great week.